How you doing? I'm Mr. Rose, and today we're going to talk about the momentum of an object that is a changing mass. This is an example of, say, a car that's driving and burning gas, a rocket, obviously, that's burning some fuel. Even you could say a car or a boat moving and throwing any mass overboard or out of the car. So to do this, I have my initial condition. My initial condition, I have some rocket that's traveling through space at velocity v. It's got an initial mass m, and that's happening at time t. Well, later on, this little astronaut decides to turn on the thrusters. So the thrusters expel this dm, this small amount of mass. And when that happens, this mass, or the thrusters, are causing the velocity to change from v initially to v dv. I'm adding a small change in velocity dv. Now I'm saying my mass plus dm is my new mass. Well, what does that mean? Does that mean that my rocket is gaining mass? No, it doesn't. What I'm doing is, because this dm, that change in mass, is leaving, I'm going to define that dm as a negative. Now this gas that's being expelled, I'm also saying there's got a velocity, plus its change in velocity of the rocket, because it was traveling at velocity v, plus, or I should say minus, the velocity of the gas that's expelled. That's what I'm defining as u. So you can see this is happening at some time later, t plus some other time, dt. And the things that I'm defining, those specific things, I'm defining dm to be less than 0. So dm is a negative. I'm also saying that u is the speed of the exhaust gas relative to the rocket. Now, in order to figure this out, I'm not sure if you can see this in red. But what we're saying is that the net force, due to Newton's third law, the net force of this system is equal to 0. That's what this says, F net equals 0. Therefore, I'm going to say that my system momentum is conserved. Obviously, there's a conservation of momentum, and we actually know if there's no net force, there can't be a change in momentum. So that's how we're doing that here. Here I've listed every possible thing I could know, because this is a little bit of a confusing example. I know that I have the mass of the rocket at some time t, I define that at m. At some time later, I define that as m plus dm. Remember, that dm I defined as negative. I got my velocity of the rocket at v. At some time later, it's v plus dv, it's getting faster. I know the momentum of my rocket is mass times velocity. At some time later, that's just my final momentum. There's the mass plus my change in mass times the velocity times my new velocity. That's my final mass, my final velocity. The mass of my gas, well, there was nothing expelled, so at time t, that was just 0. Later on, it was negative dm. That was my mass expelled. The velocity of my gas, again, 0. Afterwards, it's my change in velocity of the rocket, v plus dv, minus that, what I defined as u, that exhaust velocity. And then the momentum of my gas, to start, was 0. I just needed some more room. And then to my final was just m times v, negative dm times my velocity of the gas. Now, to use conservation of momentum, I'm going to say momentum before is equal to momentum after. This is my initial momentum of the rocket, my initial momentum of the gas, which I know is 0. My momentum of the rocket, the momentum of the gas. My momentum of the rocket is mass times velocity. That came out to be 0. Here, I've tried to color code the mass, and we got this from before. I'm just taking everything I defined and putting it into my after. Mass times velocity plus the mass of my gas times the velocity of my gas. I distributed all of that through, and now you can see where I color-coded. MV and MV, those are obviously going to cancel. My green actually is what stays. I have an MdV, M times dV. dm times v, I've got a negative dm times v from the other side. That cancels. I distributed, I have negative dm, I have positive dm and a positive dv, and a negative dm and a negative dv. Cancels. And then I have a dm times a u, my exhaust velocity. So when I simplify all of that, I've got 0 equals the mass times my change in velocity, plus my change in mass times my exhaust velocity. Rearrange that equation. Now I have this simple differential equation, dv is equal to negative u, that's the negative exhaust velocity, times my change in my new mass, dm, that small mass that left, times the entire mass, m. So what I'm going to do is I'm going to solve for this as a function of mass, because I know the velocity changes as a function of mass. So I have two things going on here. First, we're looking at that change in velocity with respect to my thrust and my change in mass. And now I'm taking the antiderivative dv from v naught to v and my change in exhaust velocity, my exhaust velocity, negative u, times my change in mass, from my initial mass to my final mass. This is easy to take an antiderivative. The antiderivative dv is just v from my initial and my final condition, which gives me a velocity, final velocity, minus an initial velocity. And that carries all the way through. The green was a little bit more complicated, but it is just an identity. I pull out my constant, negative u, from my initial to my final mass of 1 over m times dm. When I take the antiderivative of 1 over m, that comes out to the natural log of m. So the antiderivative of 1 over something comes out to the natural log of that object. So this is my identity. And I'm differentiating from my initial condition m naught to my final condition m. Negative u, now I put in my conditions, the natural log of m minus the natural log of m naught. I wanted to drop that negative, so what I did here is I just switched. I had dropped my negative, distributed that through the natural log of m naught minus the natural log of m. And I'm left with my change in velocity is equal to my exhaust velocity times the natural log of my initial mass divided by my final mass, m naught divided by m. What does that show? That shows me that it's a limiting factor. If my mass never changes, if my initial and my final mass are the same, that would give me the natural log of 1. There's a little bit of a glare here, but that's what it says here. Shows limiting case. If m naught is equal to m, that shows the natural log of 1 is 0, which means my initial velocity and my final velocity are the same. We're not speeding up. Well, what if I look at it with respect to time? In other words, what if I'm looking at the thrust with respect to time? This is going back to where I started. dv, my change in velocity, is equal to negative u, there's my thrust, dm divided by m. I'm going to separate my variables out now. mdv is equal to my thrust, negative u, times dm. And I'm going to take that with respect to time, because my velocity is changing with respect to time. So I have here m, I'm going to rewrite this dv, because you can't see it so well. m dv dt is equal to negative u, that negative u again is my thrust, times dm dt, my change in mass with respect to time. Well, dv dt by definition is an acceleration, so here I have Newton's law, F equals ma, is equal to negative u, there's my thrust of the exhaust, times my change in mass per unit time. I can say this is actually the rate at which the gas is expelled, which makes sense. dm dt is that rate at which the gas is expelled. I'm going to define that as an r. So now I have m times a, there's my Newton's second law, equals this velocity, my velocity of the expelled gas, times r, where r is the negative, because I dropped that negative, the negative rate, opposite direction, of which my mass is being expelled, and I'm losing that mass. So this is very simple thrust. I know thrust is equal to r, the rate at which my mass is being expelled, times the velocity of that expulsion. Thrust is the same thing as a force. That is F equals ma. This is really powerful, and it shows us really simply that thrust equation. I'm going to go on for a little bit longer here and give you one example. So for our example, there's a lunar mission. There's a spacecraft that's increasing its speed by 2.2 meters per second. It was initially traveling at 400 meters per second. The thrust velocity, the expelled gas is going to be expelled at 1,000 meters per second. What we're going to look for is the fraction of the initial mass of the spacecraft. And we kind of do this two ways. I hope you can follow that. The very first thing I want to do is I want to ID all of my variables. I'm going to say my change in velocity is my final minus my initial, 2.2 meters per second that was given in my question. My initial velocity of the rocket was 400 meters per second. And again, that U, the expelled gas, I'm defining it 1,000 meters per second. From the frame, or from the reference frame of the ship, my initial velocity is 0. My dv, that change in velocity, is 2.2. My thrust velocity, going the opposite direction, is negative 1,000 meters per second. That's the expelled gas. I'm defining the mass of the ship as m. The mass of the gas is at negative dm, because I wanted to define that as a negative. And that means my remaining mass is m plus dm. Okay, so this is exactly what we did before. I have my initial momentum equals to my final momentum. My initial momentum is just mv, and then my final momentum, exactly how we had it before, is my my final mass, that's m plus dm of my rocket, v dv, the new velocity, plus the mass of my expelled gas and the velocity of that expelled gas. Distribute all of my terms through, simplify it. mv equals mass times velocity is mass times velocity of my rocket plus mdv plus dm times u. We know that mv and mv are canceling out, and I'm left with 0 equals m times dv plus dm times my expelled gas, u. So if I rearrange this, looking at the left side and the right side, let's start with the left side written in black. I have my negative dv, the change in my velocity is equal to u, that's my expelled gas, times my dm over m, my change in mass. So this tells me with everything that I know, dm over m is 0.022 kilograms, which is, again, either 0.22% of my initial weight, or I'm left with 0.9978%, 0.9978 times that initial mass. That's the fraction of my mass left over. I could have tried to do it a different way. I could have looked at this and I have my change in velocity, v minus v naught, is equal to my expelled gas, negative u, times the natural log of m divided by m naught. Exactly what we saw earlier. Now I'm going to simplify v minus v naught, my change in velocity, divided by my expelled gas, negative u. Now this time I did not flip it because I wanted that fraction. My change in mass is the fraction of m divided by m naught. So I have my v minus v naught over negative u, my change in velocity divided by my expelled mass, is equal to the natural log of my final mass divided by my initial mass. To get rid of that natural log, it's just an identity. I'm going to take e, raise it to both sides. So I'm taking this e, raising it to v minus v naught over negative u is equal to m over m naught. And I come out with that exact same thing, 0.9978. Again, this is the fraction of mass that I have left over. I hope you found this helpful. Please feel free to like, comment, or subscribe. I hope you enjoy the view. I look at that all the time, but you can only see the reflection of the camera, so that's not nearly as exciting for you. Please feel free to leave questions, and I'll see you next time.